Okay, so it's really my pleasure to introduce Ekaterina Dineva, who is a researcher and postdoc at K11, and she will she's been doing quite a lot of research on solar physics side and looking at machine learning models. So we continue on a similar topic, and the name of the presentation is Parametrization of a sharp vector magnetic field using disentangled representation learning. Thank you very much.
Thank you very much for the introduction. Hello, everyone. Brief motivation of what I'm doing. So the test observation in this case are, again, pre-processed magnetograms, so something that's obtained from of the observation of the photospheric magnetic field, basically base layer of the solar atmosphere. And we are using variational encoders, variational autoencoders to parametrize this active region. So the whole idea started with, can we, there is already empirical data set which people try to use for forecasting, but this is, let's say, not enough. So people were thinking, what if we have machine learning features that we can add to this parametrization and then do forecasting? But in the process of my work, actually, the whole parametrization and understanding of this machine learning feature become a problem on its own. So one of the goals, there's, let's say several goals of why we do parametrization: just simple encoding, reducing the dimensions, feature selection, for example, for some interesting science, and which can then facilitate onboard analysis. If we're talking onboard, if you're talking on Earth, just future analysis, such as forecasting or finding flare forecasting, finding flare precursors. And this is also one of the results that I'm going to show here, where we benchmark these machine learning features with human-made, basically, empirical parameters. So variational autoencoders, I guess many of you have heard, it's not really a new model. So the idea is that you give it an input, you have the encoder, which encodes the data into a small latent space, lower dimensional latent space, and then you have the decoder, which reconstruct the input from this coding. So in this case, we're using variational autoencoders, which should give us more generalized information in the latent space, or something that is not just enough for reconstructing the image, but in some cases can be used to generate, create more data set. But in this case, we are just using it to explain the active region using machine learned features, which is basically ML features for active region parametrization. So the here I'm just showing what is actually the interest in this case. This is evolution of the active region magnetic field, and black and white are just the different polarities. Right. So there is one caveat here, that we're not only using variational autoencoder, but we are using disentangled variational autoencoder, which in principle will give a more structured latent vector. What that means that a single latent variable is sensitive or explains some part of the input or its generative factors. And in this case, in this particular case, we're using beta variational autoencoders, which basically puts this beta parameter here at the latent loss, which weighs the Kyle divergence in this case. Yes, and it's a trade-off between, how accurate your reconstruction is with the decoder and how structured is your latent space, and we are more interested in the latent space rather than the reconstructor. Okay, so an introduction of the SHARP data set. It's basically, again, SDO observations, in this case, HMI. So they observe the photosphere and compute magnetic maps from that. And it's particularly for space weather research. And they have automatic data pipeline, which basically detects regions with strong magnetic field and then create these cutouts that are later used for further analysis, prediction, and so on. Okay, so I take variation of autoencoders. I use SHARP magnetic magnetograms of active region, and then I try to understand what latent vector gives me, basically in this case, and do some kind of parametrization and discover a label discovery, because this is unsupervised. So the latent space is learned without any labels or supervision from our side. So this is a few numbers about the data set. These are active regions across the solar cycle. So they are plugged from each stage of the solar cycle, which means that we have high activity and low activity active regions. And the interesting part is that they carry different physics. And there is never a active region which is the same as any other, which makes the problem of generalization very complicated. So on the top here, just a demonstration is the original images, and on the bottom is the reconstructed images with beta, in this case, 2.5. The value is 2.5. And I will use a latent vector with 6 values, 6-dimensional latent vector, which is a very low. And then we compromise the reconstruction, but we are hoping that with these 6 parameters we can represent in low dimension the active regions and then combine with the empirical parameters, which is what's happening here. So one more word. So for label discovery, in this case, we use TSNE, which main point is to take high dimensional data, which is my result. So for each of these 50,000 images, I have 6 values, still high dimension. So I want to reduce it to something that a human can see, so a 2-dimensional map. And the good thing about TSNE is when it do the low dimensional embedding, points that are close to each other in low dimension are also similar in high dimension. And I'm not gonna talk too much about that one, so let's go to the results. Okay, so we have all the active regions, which are represented by 6 values of the latent vector. And we apply TSNE, and this is the embedding for all the active regions. So what we see immediately in the most right figure is that the latent vectors of the same active region are clustered together, so you can actually separate the active regions due to the parametrization. Another thing, if you take, if you color code your map using the information from physical parameters, so in this case, helicity and current, these are just colors. So we are using colors to find where the, for example, extreme values are. In this case, you can actually see, so where the high values of these parameters are. And then you can say, okay, I'm not interested in the rest. The rest is quite simple or quite, let's say, less active regions, but we know where the important active regions, so we can immediately focus here, take that, and then do further analysis. But this is a little bit crowded. So if we go and just looked at separate active regions, then here again the color coding is done using the although unsigned flux, that we can even see the evolution of the active region itself in the parametrization, because the points that have similar properties, which means they're similar in time and evolution, are close together in the embedding. So there are interesting cases like for O1 active region, which separates into several clusters, and this requires a little bit more analysis to see what happened there and why the parametrization saw such a large difference between the different stages of the evolution of the active region. There is another way to look at that. So in this case, I'm again putting in the x-axis, you have the total flux, and on the y-axis are the 6 latent vector values. So in some cases we have, okay, the color is also DOI, the day of the year, basically the time, the lifetime of the active region. So there are some linear relation, although not completely linear. There is some more complex relations, and in some cases we actually don't have much information. But what I find good in this case is that it's not completely linear, which means that our machine learned features have additional information. It's not just, redundant information that we could have seen already the empirical parameters. There is something more there, which can help us predict flares or understand the physical changes in the active region for purely theoretical purposes or practical purposes. And so these are some takeaway messages. So the encoding works. The feature selection seems to be also working well, and there is a potential to use these features on some kind of analysis, for example, on extreme event or something that one wants to focus during onboard measurements without, taking too much space with large images, or mainly because with at least my experience from observations with these SCMOS and CMOS cameras, the data becomes really heavy, which is good for analysis, but not always good for storage, even when you're talking about Earth cases. And yeah, that's me. Thank you for your attention.
Very much, Ekaterina. A beautiful presentation. Question, comments? Thomas?
Just I have a quick question. So those ML features, what's the best way to understand what they're showing?
Exactly. So the best option I have right now is to benchmark them, because these parameters that I show, I forgot to mention, they come with the map. So they compute a map, this active region, and then they have 20 parameters for each one. So this is so far the most complete data set that I've seen that actually comes already with human made parameter, the empirical parameters, which I can use to benchmark. So why I was using here the total flux, because it also relates to the size of the, so it relates to the physical properties of the active region. So one would expect that it also will relate to the latent vector.
And I guess in the next slide you show that there are differences between them, right? No, the next.
Yeah. So if you look into, so these are computed, for example, each point is 6 values. So if you look at the values separately, maybe, for example, you don't need these two. You can avoid them because they're maybe useful for reconstruction, but they do not bring any physical information. It's too random. Yeah.
Questions? I was wondering about the computational cost that requires, for instance, for running this kind of training high-dimensional feature extraction.
Yeah, so I need to bring probably some numbers, but the problem
just order like minutes, hours, or seconds.
Okay, so training of the model with about 50,000 images takes about 6 hours right now. It can be, if I work a little bit more on the architecture, I think I will try to reduce the layers, also the hidden layers, and see what happens. Can speed up a little bit, make it a bit lighter. The problem is with the generalization that it is not still, I'm searching for a way to do the proper generalization. If I give it images which are very far away from this, these ones that it's trained on, it can recognize different polarities, for example, but it has really troubles reconstructing the actual images. It can tell me, okay, there is two polarities and they're more like this, or like one is less than the other, but the fine features are missing. But I think this is also a property of the autoencoder.
Thank you. No more question, comments. Let's thank Ekaterina again.